So hi, as Rob said, I'm Barry, solution architect, developer. I'm based in Phoenix, Arizona, where today it is, what is it, about 45 degrees C, so that's about 114 degrees Fahrenheit, I believe. So it's a little toasty, but not too bad. It's been a lot hotter. Um, as Rob mentioned, I am the kind of person that keeps a list of his favorite physicists and favorite mathematicians. And I've been trying to come up, I feel like that makes me like a level 2 geek because I have, both favorite physicists and favorite mathematicians. But, we can work on that. Uh, I'm also a big supporter of the open independent web. So if you enjoy this talk and you thought that this was valuable to you, let me know on Mastodon or on one of the other Fediverse tools. I highly encourage that. I believe it's really important, and you could hear all about why I think it's so important if you check out David Giard's Technology and Friends show. We did a segment on that. I'm an open source contributor, and I have a number of projects that I shepherd. I'm a supporter of the .NET Foundation as an open source contributor, and also just as a member. There's a lot of good people doing a lot of good work for the .NET ecosystem there, so I advise checking it out if you don't know them. And I'm one of the founders of Arizona GiveCamp along with Rob. And so if you're not familiar with the GiveCamp, I'm betting most of you are, because if you've heard Rob speak, you know about GiveCamp. But really quickly, it's a weekend event where we put a bunch of software creators in a room with a bunch of great local charities, and we code for those charities. And at the end of the weekend, we turn it over to them, and it's just a great experience for them. We help them further their mission. And as Rob likes to say, sleep is optional, caffeine is provided. So I hope you'll check that out. Finally, I do want to take just a real quick moment to thank the organizers of these type events. I've been very fortunate that I get to do this kind of stuff, and it's because the organizers, the sponsors, and you as attendees make these communities happen. And I think there's so much valuable work and so much value that comes out of these communities. So thank you all for participating, and thank you especially to all the organizers who make this happen. Enough about that. Let's talk about RAG. And the title was that we're going to look at the future of information retrieval. To look at the future, we probably need to have just a little bit of foundation of where we came from in the past and where we are today. So let's start by looking at a typical search. What did a search look like before, say, 2013? This is my blog, Cognitive Inheritance, that Rob has just linked to. And this is a keyword search, a set of keyword search results for the query, best ways to learn about my problem domain. And you can see some articles that are, from my blog that, have those keywords in them. But they're not great. They're keyword rich, but they're not necessarily really the kind of thing that I was looking for here. So we can get some better results, perhaps, if we instead use something like a vector search. And we'll talk a lot about vector search, so it'll make a lot of sense, and you'll know exactly what that is by the end of this talk. And you'll notice that the same query produces a very different set of results. And in fact, the results themselves are much, much more relevant. In fact, event storming, the second result there, is exactly my recommended way to learn about a problem domain. So we get much, much better results from or we can anyways, get much better results from a vector search than from just a plain old keyword search. But the real power comes in combining the results of a vector search with the power of the LLMs. And I'll explain how that works as we go forward today. But what you see here is the AI results. This is, instead of giving you a list of articles that you can look in and hope to find an answer, this is a potential answer. Now, of course, it can be wrong. It's based on an LLM. But what this has done is it's taken the results, and in fact, at the bottom of the page, which you can't see there, but I've zoomed in on here, you can see that those exact same articles are linked in there. These are the sources, and those were used to generate these results. So we have a much better likelihood of getting the right answer because I brought all this information into context. We'll see how to do that as we go along. So with keyword search, the most important thing about keyword search is that you lose context. Now, maybe I should probably have you like start a context counter here, because I'm going to say the word context a lot today. Context is everything when it comes to large language models or any kind of language models. But you lose a lot of context in keyword search, because what you're doing is you're not looking at how the words relate to each other. What we do in keyword search is we break it down, we put it all in lowercase tokens, we break them down into individual words, we remove stop words like to and my. And then we do some stemming where we reduce words to their root form. So like runner becomes run and children becomes child, etc. And you can see that there's a lot of context loss there. We also have no relationship between the words. We just know that those words are there, but they're not related to each other in any meaningful way. Then, of course, we apply a reverse index search or an inverted index lookup to find the documents from the words we generated, and that's how we get those search results. And prior to 2013, that was really all we had. There weren't many other options. But in 2013, there was a fairly major breakthrough in this field with the introduction of Word2Vec by Google. Word2Vec introduced us to the idea of creating mathematical representations of ideas, of concepts. And this was one of the things that started us going down this path towards LLMs. There were a number of other things that occurred between then and now, but the biggest of them was in 2017, the publication of Attention is All You Need. Again, Google. They published this article that basically created the attention mechanism within the transformer model. And that is what spawned the LLM revolution, to the point where now, and basically since 2021 or 2022, nearly every search we do is some form of vector search, at least partially. There's still hybrid search mechanisms out there. We still sometimes use keywords, but for the most part, we're almost always at least using some form of vector search when we're doing any kind of searching today. So, knowing where we were, what are we going to talk about? Well, we're going to talk about embeddings. Embeddings are those, when I talked about Word2Vec, it was we can create a mathematical representation of ideas. Embeddings are how we represent that using math. So we're going to talk about those embeddings, what they mean, what they do for us. We'll talk about how vector search uses those embeddings to find relevant information. And then we'll talk about how RAG builds on top of that. How do we use the results of the vector search to get an answer from the LLM rather than just having to look in the articles and hope we find an answer. But of course, these are stochastic models, right? So there are problems, there are limitations, there are things that they don't do well. We're going to talk about what some of those things are, try and give you some intuition as to what things work well and what things don't, and then how to overcome some of those limitations there. Sound good? All right. So let's start with embeddings. So an embedding is just a point in multidimensional space. Now, that's kind of meaningless in no context, but if you just think about our world as a three-dimensional space, And some point in it might be representative of a particular idea, and some other point is another idea. That's what these things are. They're just mathematical representations using these vectors that describe a point in space to encode both semantic and contextual information about an idea. I'll drill into that here momentarily, but there are two things we probably want to know about this. Well, first of all, the typical model, like the text embedding ADA002 model that's listed on the screen, that is the standard model used by GPT-3 and beyond. They all use that text embedding model. There are lots of other models. I actually use two different ones myself. I use the text embedding ADA002 in production for the most part for actual operational stuff. And then I use smaller, faster, cheaper models locally to do development work. There are two features of ADA002 model. First off is that there's 1,536 dimensions in it. Now, 1,536 dimensions, first of all, I can't picture that. I have no way to, to say, wow, that's, I can visualize. No, I can't visualize anything more than 3. But it's also just an insane amount of data. I did a blog post where I looked at if we have 2 digits of precision, because they're floating point numbers. So if we just use 2 decimal places of precision, how many values can be stored in 1,536 dimensions? And then what if we did 3 significant digits and 4? And what I found is the number of, almost no matter how low a number of significant digits you use, it's just unrepresentable numbers. They're inconceivable to the human mind. Inconceivable. The other thing to know about them is that they are normalized in this model. They're normalized to unit length, meaning there's always a length of 1. And that's going to simplify some of the calculations for us. So let's take a look at what a vector really is. Let's give an example. Let's talk about one example of an embedding. So what I've done here is I've taken the 1,536 dimensions in these 3 different vectors, and I've projected them down into 2 dimensions. Now that's kind of a lossy process, but we can get a visualization and we can see that there's these 3 different homonyms or different words, different meanings of the word RAM are in different places in this space. So I've got a RAM that represents a truck, I've got a RAM that represents a sheep, and RAM that represents computer memory. And I've plotted those on the screen here in 2 dimensions. If you're interested, I used what's called t-SNE to do the dimensionality reduction. We're not going to talk about that today, but just in case you were interested for the math nerds here. So here's the 3, these are the 3 embeddings. These are representations of the 3 embeddings. Now, if we plot those next to the embeddings for memory, sheep, and truck, you can see that they're related. They're closer in space to those same concepts. And that's really all an embedding is the closer it is to a concept, the closer it is in space to other things relating to that concept. And so we can look at things like distances and figure things out from them. We can look at this and say, which of these things is closest? Memory is closest to I'm getting some RAM from my PC. So if I was checking that, if I was checking memory, sheep, and truck against that, what I'd see is that memory is the closest. We'll look at that again here in a minute. So embeddings are just a way of creating structured data out of unstructured data. We're taking the text and we're turning it into an array of floating point numbers. And it doesn't just have to be text. It can be anything that the models support. So one of the models I use locally has multiple embedding spaces. So like there's a model version that is useful for text and another one that's in the same space useful for images. So what I can do is I can get the vector for an image and then compare that and see what is the closest text I have to that, as long as I'm using that same embedding space model. Super interesting stuff. A lot of power there. And we can also do a lot of different math on this. We're going to see a lot of cosine similarity and distance calculations here today. We are also going to do some nearest neighbor search. In fact, that's what is used by the RAG systems when we go to a vector database. We'll see that later. We'll also do a little bit of clustering, running some clustering algorithms to get groupings of these vectors. We can do basic math on it, addition and subtraction. I mentioned word2vec earlier, that original model from 2013 out of Google. That vector model, one of the canonical examples that they use is that you could take the vector for queen, subtract the vector for woman from that, add the vector for man, and you would get a point in space very close to the vector for king. It just boggles my mind to think how much power, how much potential there is in all of this. You've already seen me do dimensionality reduction. We can also do things like anomaly detection, see if one vector is just way off in space compared to a bunch of others, that kind of thing. So there's a lot of capabilities here. Now, one of the tools I use for this is called LM Studio. I'm actually in the middle of migrating off this to Microsoft's, what do they call it, Foundry Local. But for now, we're going to talk about LM Studio. LM Studio is an application that allows you to load these models. Many of them are free that can be downloaded from Hugging Face. And you can run these models and execute them in your local development environment. So this is my local IDE for running models. And you can see, this is a screenshot of it. What I've got here is I've got a model loaded here, the Nomic AI embedding text version 1.5. That's an embedding model. That it's the one that I was talking about. This is the text version of the model where there is also an image version of it that uses that same vector space. Super interesting stuff. So that's the model that's loaded here. I've got a local inference server set up. So it does most of this work for me. I don't have to do much of anything to set this up. And what that does is that it enables these requests. So I can do OpenAI compatible API calls against these locally running models. And so I can run them in my development environment and do work locally to see, are things working as I expect them to. And so if I go to Postman and I run a request here, and you can see there's actually a log in here that where I did a request, best ways to learn about my problem domain, that same request. And if I go into Postman, we can see that the response I got was just this list of floating point numbers. There's actually 1,536 of them, but you can't see that much on the screen. So this is how I can test things. I can do local development work. And then eventually what I'll do is I'll publish it out to the cloud, and I'll use a cloud instance of probably ADA002 model for doing actual production work. So that's great. So we can get embeddings. We can get these lists of 1,536 or so floating point numbers. So what do we do with them? Well, we can find the distance between 2 points, between two of those vectors. So remember that these are represented as vectors. They're arrows from the origin to a point in space. That's how we represent a vector. Well, if you remember basic math or basic geometry, any two lines that intersect form a plane, which means that no matter what dimensions these things are pointing in, there's always going to be a plane there, and we can measure the angle across that plane to those between those two lines. The cosine of that distance is the cosine similarity. And then if we subtract that from 1, what we get is a cosine distance. And that means that if they're the same point, we get a 0. In fact, here's the graph of that. So the closer they are to each other, the closer the cosine distance is to 0, and then it just gradually goes up as high as 2. Now, I have never seen a cosine distance greater than something like 0.6. I've never found anything further away than that, because the words are almost always related somehow, especially if they're in the same language, right? They're always related by the fact that they're in English or whatever language. So cosine distance is a great way to measure distances between them. And so if we were to take that cosine distance and plot the vectors for I'm getting new RAM for my PC against the vectors for computer memory, pickup truck, and bighorn sheep, you can see that computer memory is significantly closer than the other two. Now, I cheated a little bit here. I added a little bit of context. Instead of just saying memory and truck and sheep, I said computer memory, pickup truck, and bighorn sheep, just to make the distances between those three a little bit greater, just to make it easier to see. But it's very clear that computer memory is the closest concept of those three to I'm getting new RAM for my PC. I hope this is all making sense. Please let me know if something is confusing. So embeddings encode this contextual information, but there's just so much that they actually represent. So embeddings recognize, or I'm gonna use air quotes whenever I say understand, because they don't actually understand anything, but it's very easy to say that embeddings understand synonyms. They understand that happy is closer to joyful than it is to sad. That's encoded in there. So you're going to find them closer in space. But it's also true for things like language. The vector for the queen is very close to the vector for la reina, the Spanish word for the queen, right? So if words have the same meanings in different languages, they're going to be very close to each other. Not the same, because they differ by the language and potentially other things, but very, very close, because they're representing the same concept. And this is one of the things that makes me think that we have just barely scratched the surface in what we are capable of with these models. I feel like we'll be able to find things, find information, create, synthesize, come up with ideas that humans cannot come up with, because, well, let me give an example. Suppose there was a physicist that did some work with lasers in a particular field. And there was also, and that's a German physicist, and he wrote his papers about this concept in German. And there is a French dentist that uses lasers in his dental practice and had a complementary concept that was exposed in his writing. Meanwhile, level 2 nerd here back in the United States only speaks English for the most part. And I'm trying to build a lightsaber so that my cat, happy National Kitten Day, by the way, so that my cat can grab it and run down the stairs. And you've seen that video, right? And so if I'm asking questions of the model, if it's been trained on both those papers, even though one of them was in German, one of them was in French, they're on two completely different subjects. One's on dentistry, one's on, astrophysics or something. I still get all of those concepts understood by the model and can potentially result in information that is valuable to me. I think the potential for these things is simply unlimited, and I'm hoping we find ways to use that for good and not for evil. So there's other things that embeddings represent. It understands, again in air quotes, that idioms, that he kicked the bucket actually means he died. And what you'll find is those two things are very close in the space, in the vector space. And even though he kicked the ball is semantically almost equivalent to he kicked the bucket, it's much further away because he kicked the bucket does not mean he actually physically went up and whacked a bucket with his foot. It understands sarcasm. It recognizes that, well, look who's on time is closer to actually late than actually early. It knows that bark, the sound a dog makes, is closer to a howl than it is to the bark of a tree. So there's just so much here that so much encoded here. We need to find ways to figure these things out. And here's how we would do that. Because in order to be able to do these kinds of comparisons, we don't want to be getting the vectors every time. Running them through the model, it's not expensive, but it's certainly not as cheap as doing a database query. So we're going to want to get the vectors once and then store them in a vector database. And then we can do very, very fast retrieval. We can do a lot of the operations we're going to do on them once we've grabbed those vectors once and put them in a database. Now, when I created this slide, maybe a year and a half, 2 years ago now, there were not that many. There were a few key players in the vector database space. Now, pretty much every database is a vector database. So whatever you happen to be using is probably going to work for you if you're trying to do these kind of things. So don't worry so much about, is my database a vector database? They almost all support it now. And they leverage a data structure called a KD tree or a K-dimensional tree. Now, a K-dimensional tree is a binary tree that you're probably familiar with is just a single dimensional version of a K-dimensional tree, right? It's just a specific implementation. And the way the K-dimensional trees work is instead of just, remember, when you use a binary tree, you split the problem at every level. So you say, is this side or this side? Okay. Now the next one, is it this side or this side? Well, KD trees do that, but they roll through the dimensions each time. So the first layer might be the zeroth, the first index, which is the 0 level, and then it's going to split the problem at the next level on the first index, and then on the 1 index, and then on the 2 index. So it's going to roll through the indices until it finds what it's looking for. And these are super useful and super fast. They can do binary searches in log n, order log n time. So very, very fast. Now it takes a little bit longer for construction, that's n log n, but that's usually done in the background. So you probably want to update your database in the background, and then when you have a user sitting there in context waiting for a response, that you're just querying it and using, getting the response very, very quickly. And this is how we do nearest neighbor search. So I mentioned that once already. Nearest neighbor search is where I'm going to say, here's a vector, find me the closest other vectors to this vector. So if I've got millions of records in my database and I get an embedding for, the queen, it's going to return the closest vectors that it has to that embedding. That's a KD tree, and that's how we do, that's how we use our vector databases. And that is how we do vector search, right? We're finding the closest vector to a query vector. We get the embedding for the query. We have to do that in real time probably because somebody has just typed it. We get that embedding out of the model, and then we run the nearest neighbor search against our database to say, hey, what are the nearest neighbors of this? And as I mentioned, it can work with nearly any type of data as long as I have an embedding model for that. But it is still a stochastic process. So we should recognize that between executions, it could vary. may or may not, depending how the database is implemented. But it will definitely vary between models. So if you use locally, you use a particular model and check the embedding, the what's the nearest neighbors that way, and then you use a different model in production, you may get different results. Now, of course, you always have to compare apples to apples, right? You have to have, if I'm using a local model for my embeddings locally, I have to use that same model to get the embedding for the query. And likewise, in production, you always have to compare vectors from the same model. But even if you're doing that, if you change models completely from one, from locally to in production, you could get different results. So you want to be careful of that. Let's look at an example of doing this kind of nearest neighbor search, or using these embeddings to calculate distance and doing some work with it, and see if it maybe produces some problems that we might need to take into account. So this is these are the exact, these are resumes for a Java developer that were created based on a listing that I pulled off of, from online. I like to make fun of Java developers, so, it is what it is, right? And these are exactly identical except for two things. The name and the location of where they went to school and where they had their first job. Everything else in here is exactly the same. They live at the same address now. They work at the same company now in my location here in Phoenix, Arizona. They've done so for the exact same amount of time. Everything is the same except for their names and the locations of their school and their first job. Anyone want to predict who, if we get the embeddings for these two resumes and the embedding for the Java position that I pulled offline, which one's going to come closer?
I'm going to assume London because it's a bigger market.
It is London. It is probably, well, that could be part of it, that it's a bigger market. Very good call. As it turns out, Armando's resume comes out about 12.7% worse, further away than Jonathan's does. And to make matters worse, this is the part that I find the scariest. If Armando had 2 additional years of experience, meaning he started school 2 years earlier and everything was, 2 years longer, his score only increases by about 1 point. He's still, Jonathan is still considered a better resume, even though Armando has 2 additional years of experience. So there's a couple of reasons for that. Number one reason is we're not doing the important stuff. We're not doing the attention mechanism, which is the thing that tells you what words are important, how words relate to each other. We're cutting this off. We're only doing the embedding piece here. Now, this is a representation here of the transformer model. So if you're running ChatGPT, this is the model you're putting it through, and we've got some sample data elements in there. I go into detail on this in a different talk. But we're cutting it off. We're only doing the part in red up here. We get tokens and then we get the embeddings. So we're not doing the piece that could help by determining what's more important. But even within that, as you pointed out, the United Kingdom is much closer to the USA than the Argentine Republic is. And you can see they're actually both fairly far away in space, but UK is considerably closer to the US. And of course, it depends on how you embed it, what exact phrase you use as to how far away it is. But it makes sense because there's so many differences between the US and Argentina versus the US and the UK. We have a shared cultural and political history. We were a colony of the UK. I don't watch a lot of TV, but I certainly haven't seen any Argentine America channels where I watch BBC America for Doctor Who all the time. I guess they don't really show Doctor Who anymore, anyways, but we have a lot of shared uh, history and politics, et cetera, with the UK. And so we are going to be closer in space with them. But what about the numbers? Why, when we added time to Armando, did he not get better? The answer is going to scare you, I think, or at least I hope. This is a graph of the cosine distances between the number 0 and every number up to 1,000. So here in the middle is the cosine distance between the number 500 and the number 0. And as you can see, they are not linear, right? In fact, I suggest that we only got lucky that adding 2 years to Armando's resume made it better. It might have made it worse. These models use math, but they are not math models. They don't do math. They are text engines. And what they're good at doing is predicting the next token. They predict what the next word or phrase might be that somebody might say. So if somebody has done the exact same problem that you're doing, you might very well get the right answer. But they're not math engines. And unless the model has been trained as a math engine, now you can use tooling, there's other ways to use them for math. But just the basic model, including the embeddings, don't try and use them for math. They're not good at it. I hope that point's made clearly because that's super important. So what can we do instead then? If we can't compare these two resumes like that, how can we compare them? So there's a couple of things we can do. We could do some clustering, right? Maybe if we run a clustering algorithm, and clustering is an unsupervised machine learning process, which makes it sound like it's really fancy, but all it's really doing is trying to find these centroids, or what they call it. Now it's centroid because it's in multidimensional space. But it tries to find the center point of these groupings, and it moves those centroids around and it changes the groupings around to try and get the best fit. And so what you can find here is if we get a good grouping, we may be able to identify what those different groupings mean. So maybe one of these ovals here, now projected down into two-dimensional space, of course, maybe one of these ovals represents Java developer resumes. And so maybe we can just use it that way to say, let's filter the resumes, but not rank them based on that. So we can eliminate a lot of resumes that are not for Java developers, but we could, but then we're not going to say this one's better than this one based on that. That's good, that's better, but we can do even better. We can do more. I mentioned that we cut off the model before we actually use the attention mechanism. But we can actually run these against that model, that attention mechanism, and leverage that. So suppose we said, you, LLM, are a resume scanner specializing in software engineers. And what you're good at is summarizing their key skills, and you omit durations and demographics like age and location and that kind of thing. And if they summarize this, now, there's no guarantees here because this is still a stochastic process, but in theory, those two resumes should summarize to the exact same thing. And then if we get the embeddings for these summaries, they should be basically the same. We can actually do that even one better though. We could do a combination of the two and say, let's get the embeddings for the resume and get the embeddings for these summaries and run them through a clustering algorithm. And then if the resume and the summary of the resume are not in the same group, that should throw up a flag, and maybe we need a human in the loop for that. So there's a lot of opportunities. There's a lot of ways we can go about to use these models and leverage them and let them do what they do well, as long as we're being very cautious about how we treat people and how we should probably have a human in the loop whenever, harm to people can happen. All right. So these are ways we can leverage embeddings and vector search. It gets even better here when we start bringing in retrieval augmented generation. Now, the reason this is so effective is because it combines those benefits of retrieval-based and generative models. So we saw this at the very first demo I gave, where we looked up articles from my blog and we used the information from it to generate an answer. That's retrieval augmented generation. We find the nearest neighbors of the query. We pull those articles, we use them, we put them in the chat context, and then we can ask a question against that with that information in the model, in the chat context, giving the model the best information we have available in order to be able to answer the question successfully. There's potentially unlimited use for this. So rather than going through all of that, let me introduce you to a good friend of mine. This is Barry. Barry is the Barry bot. Barry has been trained on my blog. And so what you saw earlier, this is Barry doing his work. So if I'm getting an answer here from, the LLM, from my, a search on my blog, that's Barry in action. And as I mentioned, it pulls up those same sources. So let's look at what the code for Barry does. And this code is already out on GitHub. There's a link to it at the end of this presentation, so you'll be able to pull down this code and look at it yourself. If you have an OpenAI account, you'll be able to connect it up and use it. This is the flow for Barry. I want to say it's super simple. I want it to be, there's really not a lot to it, but it's not just purely get the answer, get the model, get the data, and get the answer. There's a little bit more to it than that. So let's drill through this really quickly. We start with the user query. So the user asks the question, what's the best way to learn about my problem domain? In the first diamond here, the only diamond here, there is no existing context the first time through. There's no existing context. We haven't had any chatting yet. This is just the first query that we're giving it. So there's no context, so let's skip that for now. Now we get a query embedding. So we get the embedding for that query, what's the best way to learn about my problem domain? And then we bounce that off our vector database. Now this vector database has the paragraphs of my blog. That's how I chose to chunk it up. So I got embeddings for each paragraph in the articles of my blog. And so what it's going to pull back is maybe the 5 nearest paragraphs. Then I take those, I get I do a deduplication on that. So we have, we just down to a few article IDs. It stores in the vector database, it stores both the vector and the article ID that it's associated with. And once I've deduplicated that, now I can just load those articles from my content database. So I pull those articles into the context, add it to the query, and then ask the question. So now in that query context, there's all of that information, and then ask the question, what's the best way to learn about my problem domain? And we get an answer. But we're not, the users can do other stuff. This is a chat context, right? Even though chat context is kind of boring. Users can ask additional questions. They might say something like, whoa, tell me more about that. Well, tell me more about that has no context to it, right? There's no information. If I get an embedding for tell me more about that, There's really nothing it's going to be close to because there's no information there. So in that sense, what we do is we do a disambiguation. Since we have additional existing context here, what I've done is I've used a faster, cheaper model and said, disambiguate that query in the context of this entire chat. Then it gives me, and we'll see what that looks like here in a minute, that gives me an answer that is or a query that has much more context to it. So now it's going to tell me more about that thing, whatever it was we were just talking about. Now I can get an embedding for that, get the vector results, and bounce that off my content DB and give it an answer. So let's see that in action. This is the Ask Barry CLI. And you can see I gave it that same query, best ways to learn about my problem domain. And here in number 5, it says you can conduct workshops to extract knowledge and blah, blah, blah. So it tells you some ways of learning about your problem domain. It's giving you an answer. Now I said, tell me about these workshops. Tell me about these workshops. And you can see it answered, well. Certainly workshops are a highly effective way, and it talks about, some of the things you can do about it. And it talks about domain storytelling and event storming is my recommended way. The way it did that, what it actually returned from that disambiguation is, in this case, can you tell me more about the specific workshops that focus on learning and understanding the key concepts, blah, 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 about learning about my problem domain. So it was able to take that context, disambiguate the query, and go from tell me more about these workshops to tell me more about these workshops that help me do the thing I'm trying to do. And now it has context to answer the question. I'm not going to go deep into the code here, but you can see it's pretty straightforward. The entire solution is out on GitHub, and you'll see the link in the back at the end of this talk. So this is where I talk about how we want to use these things. Because the fact is, we're not really doing search anymore. We shouldn't be using search engines anymore. Even Google and Bing try to give you AI answers rather than a list of documents, for better or worse. But our applications, they really shouldn't be search engines. We shouldn't be expecting our users to search for the information they need. We need to be building applications that are radiating information. We have to make sure our users have the information they need when they need it, even before they know they need it, ideally. In fact, the ideal version of these models is as an assistant that kind of goes out and gathers all the information you need in real time and can present it to you so you can do things right there when you need it. So we need to rethink how we do our applications. This is enabling a lot more than just LLM spew at the top of our apps, although that is certainly an option. We need more than a query. And in order to do that, we need to leverage all of the context we have. We leave a lot of context on the table. There's a lot of information that we know, and whether or not we should know it, we have to be very careful about user privacy and all that. That's important, and I don't want to make it sound like I'm glossing over that. But the things that we know and our users have allowed us to know about them, we need to leverage that when it's appropriate. And there's a lot of these contextual cues that we might not think about. If it's, what is it now? In Arizona, it's 6 p.m. on a Thursday. So it's a work day, but it's after hours. Does that give me additional context for what I'm doing? right? Am I on a phone versus a computer? Where am I? Do I know information about this person's interests from the past? Do I know their preferences? That kind of thing. There's a lot of context. And if we feed that context into the models, it could do a much better job of answering our questions and giving us relevant information. Now, I have an example here of a car dealership in Tolleson, Arizona, that has a line of business app for that they use in their reconditioning area. So, for example, they have all these cars that are sitting there, and some of them are pending inspection or in inspection or what have you. And there's a lot of this. Probably looks like a lot of apps every one of us has built over the years, right? There's filter criteria. They can sort it by the headings. Pretty standard stuff for an operations manager dashboard. Cool. But we also know one thing. We know who's logged into this. So this is Bentley. Bentley is the operations manager who's logged in right now. And we know things about him. We know his pronouns. We know how he prefers date formats and things like that. But maybe most importantly, we know his role within the company. So we have information about the operations manager role within this company. We know what their key responsibilities are. We know what primary goals and metrics they have. So we know a lot about what he cares about to get the job done. Can we leverage that? Can we use that and make sure the model knows those things to make better predictions about what Bentley cares about? So we know a bunch of things. We know his job role and description. We also know that he's at the Tolleson, Arizona facility. So we know what the weather is. And obviously this weather was a few months ago. Certainly isn't now. We know things about the traffic. We can find out about traffic in that area because we know where that dealership is. There's all kinds of things. We might know information about the customer that is involved with that vehicle. So is there a purchase propensity for that customer or something like that? Do we have survey information for either Bentley or for the customers that are involved? There's a lot of information we have. And so we can take that and we can put that into the context and get information out of the model. And we can do this in the background. So maybe our application looks more like this, where instead of just giving Bentley a screen that says, here, go ahead and try and filter and sort and do things and figure out what's important, here we're giving you a bunch of things right up at the top that tell you what's important. So there's a lot going on there. And even better, in an ideal world, we'd be pulling a lot of that information together. So we could maybe find out, oh, this Mazda 3 with that inventory number, let's pull in the information about that. So if he needs it, he can access it easily. A lot we can do. And I think this is incredibly important. I've been trying to get people to remember this and to think about all this context that we have that we're leaving on the table right now. And so I came up with an idea. I said, all right, here's what I'm going to do. I'm going to make a meme out of this. So, this is first time memer here. So, help me out, support me on this one. Yo, dog, I heard you like cooking, so I calculated some recipes from your shopping list so you can turn that grocery haul that I know about into a Michelin star meal. Okay? It goes out and it says, you have a shopping list. I know about your shopping list. I can go out and get recipes for that without you even asking. Though my favorite is, I heard you like Apple products, so I ordered you a ladder so you could reach those elevated features. I keep waiting for Apple to invent the touchscreen. My machine is a touchscreen, but apparently Apple they haven't invented that yet. So anyways, I'm still waiting for that. keep in mind that we have a lot of context and we should be trying to use that when appropriate, respectfully, of course, but in ways that help our users, give them the information they need. So consider carefully what context matters to them and try and include that whenever the opportunity presents itself. So the other thing we have going for us these days is MCP. So you may have heard about MCP. It's fairly new. It's something that's come out of Anthropic very recently, and it's primarily a standard for interfacing with tooling. So your tools can build against the MCP standard and can call other other tools, can call APIs and do things like that. But you can also use those. You can create MCPs that will allow other tools to use your information. And if what you have is an MCP that is getting data, say, suppose I have a Berry MCP, imagine that. And I can plug that into any tool that respects MCPs, that knows how to speak that language. And now it is enabled to go out to my blog and search that information. So we have a lot of possibilities here and a huge amount of potential, and we've only barely scratched the surface on it. So my challenge to you then is think outside the app. Figure out how we can leverage these tools to create amazing experiences for our users that move beyond just tables on the screen or even just chat boxes. We can do a lot more, help make our apps into information radiators. And I threw in an example here of understanding the user goals, like Copilot suggestions. So if you're in a chat context with Copilot, one of the things it will do is give you suggestions for some of the things you might ask about next. These are, and a lot of times what I find is the exact thing I wanted to ask next is right there, and all I have to do is one click to get to it. Think outside what our typical experience is and start thinking about these applications in these different ways. I'm going to pause here and let you shoot this QR code that will get you to this slide deck that's out on the web. And that's where you can pull down the code base, the code for this and other AI demos is here, as well as documentation for it. Some articles I've written, some documentation on the OpenAI client and Semantic Kernel. Those are Microsoft's primary clients for leveraging AI. And then my favorite part of this is Dr. Sagan, who was on my list of favorite physicists, in case I didn't leave that up long enough for you to see it. But you'll see it when you pull down the slide deck. There's a video where he talks about, from the 1980 Cosmos series, where he talks about reasoning on higher dimensionalities. So if you're trying to think beyond 3 dimensions, he talks about how to go about doing that. So I find that super interesting. I'm going to go on and sum up here, but we'll come back to this slide here in just a few minutes. Embeddings, just these vectors, right? Arrays of 1536 floating point values, 1536 or whatever the size is of the model you're using. It's a numeric representation of generally unstructured data, so it can be text or images or what have you. And it represents both the semantics and the context of that data. And we can do math on it. So we can add them and subtract them, we can cluster them, we can find the nearest ones, and that's super powerful. We can use those in a lot of ways. We can directly measure distance. We can do clustering, or we could even use these as feature inputs for machine learning models. So if you want to take different, text or images or whatever and train up machine learning models, you can use the embeddings for those values as inputs to your model. Super useful. And then, of course, we have RAG, which combines the benefits of both the retrieval and the generative models by allowing us to fetch data that is relevant, put it into the context, and use that to get an answer. And of course, there's lots and lots of uses for that. We've seen a lot of them already in our space, but I think there's nearly an infinite amount more to come. And I'm hoping that it will be people in groups like this that will try and use these things, that will create solutions that aren't just extractive of our wealth. Let me say it that way. So it's up to us as technologists to create solutions that use these tools and give the users the benefits of these tools without being evil. Otherwise, the only choice people will have is the big corporate solutions that are extractive and honestly somewhat evil. So I do hope that this has inspired you a little bit and gives you some understanding of what's going on. I'll go back to the resources slide so anybody who hasn't shot that yet can get to it. And I'm happy to hang around and answer questions. Thank you very much.
Barry, you are always amazing. This was incredible. Thank you for this.
Happy to.
You're talking about storing vectors in databases. Does that mean that to store the 1,536 vectors, I need 1,536 columns in my database to put in a vector? How do I store them?
Well, fortunately, all these databases that are vector databases now have a vector data type. So no, you don't need to. It will usually be a single column. Yeah, that's really all there is to it. You'll have a vector column that will, and depending on how big your model is that you're using, it might have to expand or what have you to be the right size. But ultimately, it's an array of values, and the databases know how to store arrays of values.
That's cool. That totally solves it. Thanks.
Mm-hmm. Who else has a question? Can we expect to see an AC Gift Camp this year? Great question. Not this year, no, but potentially next year. That's what I'm hoping for. I'm hoping for 2026.
I've got a question. For those 1,500 plus values, and sorry if I misremembered how many there was, the bounds of those values, I know in your chart, I think it was like negative 1.5 to 1.5 plus. Is that the bounds, or would it be like the bounds of what a float can be in C#? Or whatever your database is.
To the model. So most of the models are going to be different. Like in this case, I was pulling it back in. Well, I guess I wasn't. This was just a. How did we do this? Okay, yeah. So this is just what was returned straight up from the model. So you can see that that's a pretty significant precision there. But if I load it into C#, it may lose precision depending on what type of what data type I put it into. But it is. I think it's -1 to +1. Is what you're going to
understand. And is that typical -1 to +1, or it varies based on the model, if you will?
I believe it is. As far as I know, every model that I've looked at has that. I believe that what they are doing is they're actually normalizing it to that. So whatever range that their model comes out to, they're going to normalize it down to that value, to a -1 to +1. I've never seen one that wasn't that. So.
Thanks.
Sure.
Hey, I got a question. Can you guys hear me?
Yep.
Hi, Barry. All right. So I understood that the embeddings themselves are created when the LLM is pre-trained. In some cases, for some LLMs, and then for some LLMs, it's not that way. They use a predetermined embedding. So if you look at if you look inside each of these values, like you have on your screen there on line 7, right? That number right there for that, one of the values of this 1,536, it could represent things like, say, sad or happy, or as I understand it, it could represent something that we don't have a word for. Okay, can you explain more about this? I understand. Yeah, go ahead.
Oh, it's a great question because I had the exact same question, which is what makes it a great question, by the way. Yeah, I actually did some research on this, where I was trying, like, I would take words like I mentioned the Queen and La Reina. I said, all right, let me compare those two vectors to find out which one of these array elements is the one for language. And what it turned out was more than half of the embeddings were changed. More than half of the dimensions were changed. There isn't one single thing that represents one single thing. It's the whole thing is, it's a holistic process. And so I don't think there's a way to say this is the sadness. Now you can think about it that way logically, and it makes sense, and it's a good way to help yourself understand what vectors are, but it doesn't do that in reality because these are computers. They don't think like us.
What I understood, and I could be wrong about this, but I thought I read somewhere where the LLM itself, as it's being trained, decides what each of those values are for. Just like backpropagation updates the weights in a neural network and you don't know exactly how it's going to do it, it's the same way here. Just it does it, it decides its own. Okay, I have another question for you. I maybe I got this wrong, but I remember when LLMs, like it was GPT-2 and 3, they had a higher embedding size, and now it seems like the embeddings got smaller, like there's 1,500, and I think there's one of them that's like 3,000. I remember them being closer to like 30,000, 40,000. Am I remembering this wrong, or is there something happening where the embedding sizes are getting smaller?
It's not the embedding size. What I think you're remembering is the context window size. So and that's interesting too, because that's an order n squared operation. When you're running, let me get back to the model, the transformer model here. Where is it? Nope. It's here somewhere. So in the transformer model, there we go. Okay. Can you see my cursor, by the way?
Yes.
Oh, okay, good. All right, what was I trying to say here? This attention mechanism, right? This relates words to each other, okay? So in order to be able to do that, what you have to have is basically an array, a grid, right? That has each token, and it's broken down by tokens, which is, you can think of as a word, but isn't necessarily a word. Each token is represented in a column and in a row. So you need, in order to say this word, does it attend to this word over here? And so what it is, it's an n squared in operation in memory. So for every token, you have to have that many squared bytes or whatever data structure size you're using in order to be able to use it. And what they talk about the number of, oh God, I actually had this all, I actually had written this down at one point. The number that they measure the size of a model using they use the context length as one thing, but it's also what the number of
Oh, you know what it was? It was the number of tokens. The total number of different tokens in the LLM was like 50,000.
Well, all right. So yeah, the tokenization models can be different size.
Yeah.
Like I think the one that I had, the one that I tend to use is the 100K model. So that's 100,000 different tokens. But there's a number of what? Wow. If I think of it, I'll post it in the chat as we.
I think you were right before you brought up the slide. I thought you were saying something about the context window, the context length.
Yeah, because the context length squared is how big the data structure has to be to hold that, which is why your context lengths don't get that much. You've got some that are like 10,000, but they don't get that much bigger.
Okay. Yeah.
And they're actively doing work to try not to have to use all of the context length, because the more you get into, like, it's, especially if you want to make a small size model, if you want something to run on one of these devices, you can't have an order n squared memory usage operation going on. What was it? It was number of the, if you have these things, your number of what? I'm gonna ask the LLM. Let's try Copilot. See how it. Don't fail me, Copilot. What's the measure for the size of a large language model?
Sorry, I can't do that. How about I help with something else?
Copilot doesn't think it can help with that.
Oh, I think is that the parameters, the number of weights and the total weights added up.
That's
Yeah.
it. Yep, that's it.
Yeah. Yeah.
The number of parameters that you have to train. So weights and biases. Thank you. Can't believe I forgot that. Yeah, that's what their typical usage of a model, their typical size metrics for a model, and there are many billions in the current models. So that was a very roundabout way of sort of almost answering your question.
No, I think I had multiple questions. You answered all of them. By the way, that was a great talk. Thank you.
Thank you.
I've got another question. Not maybe like in direct scope of your talk, but I figured it doesn't hurt to ask anyway. So like, mind you, I'm not a user of Copilot on day-to-day basis, due to like work constraints, if you will. But based on the amount of context that it can have, is it true, like, if you have a monorepo of, let's say, like 70 different folders and it's like 250,000 lines of code, is not all of that in context, and that's why they just kind of have the active tabs that's open for the context? Is that true? And like, how is that amount of context determined on like what the max is? Like, if you had like a hello world web API of just 3 files, like, could it just keep all of that in its context, even if you didn't have all of the tabs open at the present, if you will?
Yes, that's exactly right. Your context window is limited by the size of the model, based on what I was just talking about, because it's an order n squared operation in terms of data size. And so if you have a large monorepo, it's not going to be able to include the whole context for it. It just simply can't. If you've used Claude Code, it actually does a really, really good job of telling you, all right, here's, first of all, it tries to only look at the relevant files. So it'll do searches and things to try and pick out what's important based on what you've asked it. But then you can also, it'll tell you, here's how much of your context window you've used up, and it'll allow you to compact it. And what you'll find, which means basically, it tries to figure out what's important and eject everything that's not important. And what you'll find is that it is not nearly as good at solving the problem you were working on after a compaction of the context than it was before, because it loses all that context information.
Thanks. And does that workflow sort of sway your thoughts in regards to monorepos being less strategic, if you will?
It hasn't yet, because I really like them. So far, I still tend to build them, but I tend to build very, very small services. So what from a monorepo for me is going to be something like a web API at the front end, a business rules service that's running, it's a microservice that runs in between that may be connected by Kafka, a database structure like Cosmos DB, and then maybe an output on another Kafka topic or something like that. So it's a monorepo. It has a lot of different little projects in it. but it's only got 2 or 3 deployment units in it, and it's not huge anyways. But yeah, if you're going to try and build an entire monolithic application with all of its dependencies and all of the bits that go into it, you're going to have a tough time using these tools.
Makes
Or a
sense.
tough-
Thank you.
What else we got? I know there's more questions.
Well, I have a question I'd like to ask everyone who works in AI, but it's not related to your talk. I'll wait till later, unless we have nobody else.
I didn't hear anyone else chime in.
What are your feelings on AGI?
We
Where do
don't
you
have-
think where do you think we're going? Are we going to get there? And what do you see in the next 20 years?
I don't think we're going to get to AGI in the next 20 years. I'm not convinced it's possible, but I'm also not convinced it's impossible. A lot's going to depend, I think, on how our brains actually work, and we don't know. If these things are actually close simulations of how our brains work, then yeah, they're going to surpass us in 20, 30, 40 years. I don't know. I don't think they are. I think they are just they're just machines. They're very good at what they do, but there's always going to be a need for people in the loop. And there are things that they simply, at least based on how they work today, can't do. But do I think that in an infinite future we're going to have these powerful things that can do whatever we want them to do? It's always a possibility. I don't think it's going to happen in my lifetime. I think there's a lot of hype out there, both in the positive and in the negative, that I think is just plain wrong. So, be careful what you believe, be careful what you listen to. Most of the things that I'm convinced of it because of the work I'm doing on it directly. I don't believe there's not too many people that I feel like are authoritative on these things. So don't believe me. Try it for yourself and see what it does. I'm sorry, that's the best advice I have, which is not very good, but.
Oh, that's good advice. I feel like it's like in the movie Terminator. Do you remember in that movie the company achieved super intelligence? And in order for that to happen, what they needed to do is someone from the future came back and gave them the technology. That's how I feel. Where I may have been in the industry for so long and working with apes. I don't see it happening, but I see it happening a lot faster than I did 5 years ago. And I feel like we need that in order to get to AGI. It's like it's such a huge step, and that's all everyone talks about anymore. You look at all the marketing for all these AI companies. Yeah, we're going to AGI. OpenAI has been talking about it for over 2 years now, and they're version 5. Anyways, I agree with your sentiments.
I fear that a lot of that is intentional misdirection, right? They're saying, look over here at this AGI thing while we hoover up all your private data and that kind of thing, right? It's a distraction, so I don't know what to believe exactly, but I'm not convinced of anything at this point, and I certainly don't think we're anywhere close to actually having real artificial general intelligence. I think we're probably closer to having mechanical Turks that are actually sitting behind the scenes typing stuff in. And yes, I agree, Isaac. A lot of that is also for investors. It's we have to get we have to keep the stock price going up. So we got to keep talking about our big advances in AI that are just vaporware. But the fact is, as you've seen, there's huge potential here. There's a lot we can do. I just don't think any of it is AGI.
Question around the privacy of data and having the data actually leave the company versus the data staying on site and then having whatever learning or models or whatever, all that needs to stay on site for the company. And I think that's, you know, a concern even outside of a company, privacy, but, you know, working for, you know, the feds or banking, financial, where that data cannot leave, and the difficulties around training the data and, you know, using, you know, cloud services versus, you know, server and processor that's, you know, private cloud. Maybe you could answer some questions around that or
It's a good. I do have other talks where I go into, you know, privacy concerns much more deeply. One thing I should have mentioned and didn't, I don't think, is that embeddings are not secure. So if you're storing an embedding, it could potentially be reverse engineered. There are already models out there that can do some of that. So you can't just depend on, you know, on embeddings or what have you to protect privacy. So number one thing I think is don't include real privacy. You know, don't put some people's social security numbers in your embeddings. There's no reason for it. It doesn't help you. If you need that, look it up later when you need it, because you don't need it as part of the query context, right? So for the most part, our query contexts don't have to have that kind of information. It can be more general than that. It can be they live on the 3500 block of, you know, Maple Street in Phoenix, you know, that kind of thing. That tells you everything. Or maybe they live in this zip code. You know, that tells you what you need to know to get them weather data or traffic data or those kind of things without actually having to have private information in it. And I would avoid private, you know, that kind of, you know, especially PII, but even anything sensitive at all, avoid it at all costs if you can, and just simply don't use it. That said, there's going to be some storage that you're going to need. Sometimes you'll have to persist some of those things for various reasons. I don't know that private clouds or on-site or on-prem stuff is actually more secure than cloud. In fact, generally, I think the clouds, they do a really good job of you know, doing best practice security where you don't have to worry about it. So yeah, they're professionals at that kind of stuff. I'm not. Take that for what it's worth, but yeah, I be real careful. Did I answer your question?
It's a big question.
It's, I'm glad we're thinking about those kind of things. But yeah, I definitely don't have all the answers for that. What did Frank say? 100% of the infrastructure in RD spent at those organizations. Oh, yeah. Yep, got to keep up the hype cycle. Otherwise, they don't get their money. But like I said, there's real potential here. If we can figure out how to extract all that how to extract that knowledge out of those things. I mean, they've been trained on billions of tokens. And all of that data is in there from all the different languages and all the different you know, fields of study. How do we get it out? And right now, the only things we have, the only tools we have, I've kind of, shared a lot of them with you, clustering algorithms and nearest neighbors and those kind of things. But you can't just reach in and say, what is at this location in space? You can only say, what vectors do I have that I've embedded that are near to that location in space? So it's not a simple process to extract that information. And the more we think about it, the more we try and figure out ways to extract this information, I think the more value we'll get out of these tools.
Thank you very much, Barry.
Okay.
It was an amazing talk.